Hi guys, couple more related rates problems. So in this one, the picture is a little hard to tell what's going on, but this is a pool, and it's rectangular, but there's a shallow end and a deep end. Pretty normal for a pool if you've been into a swimming pool. But basically, what we're dealing with here, so we have a rectangular pool like lengthwise. We can't really, or I should say the depth. Okay, so going back like into the paper. Okay. The pool is 10 meters long and 5 meters wide and has a depth of 3 meters at one and 1 meter at the shallow end. If water is pumped into the pool at a rate of 0.3 cubic meters per minute, at what rate is the water level rising? When it is 1.5 meters deep at the deep end. Okay, so let's think about here what we know. Okay, so again, here, cubic meters, that automatically means that's a volume and it's a rate, so that is going to be our dV dt. Okay, so something to recall, volume of anything, other than kind of our circular shapes, is always the area of the base times the height or times the depth is another way we can think of that. So here I have a triangle, and if I go back into the paper 5 meters, that's like the depth. So we're going to take our volume formula, and we're going to say that it's this triangular prism, which the area of a triangle, right, is base times height. So for us, that's going to be like the h and the l. So we're going to do h times l divided by 2. So that's the triangle part. And then times the depth, which for us is going to be 5. So that's how deep the pool is. So we can see the 5, the 3, the 1, but we're missing is this guy, the 5 meters wide. So that's where this comes into play. Okay, so something else that we're going to look at is something we kind of did this in the last video. What are we looking for? So we're looking for at what rate is the water level rising? So we are looking for dH dt. Right? That's what I want to find. dH dt is the height of the water. We want to know at what rate is it rising. Okay, and we have a height that's given to us. So again, if I think about the variables, so I have this. I've got 5 halves HL, right? So I have dV dt, I'm looking for dH dt. We don't really have anything in terms of L. So it'd be nice to not have the L in my equation before I find the derivative. So let's look at the L and H I do have to start. We have initially that the L is 10. So I'm going to say L over H. Okay, the instant I'm given here is I have 10 and I have 2. That's the water level. So we're going to say 10 over 2 is that ratio. So again, I can think of it as L is 10 over 2 or 5H. So we're going to take this and we're going to plug it in for this L right here. So then when I do that, I've got 5 halves H times 5H. Or V equals 25 over 2 H squared. Okay, so now when I differentiate, I only have 2 variables, and it's going to deal with those 2 rates that I care about. So dV dt equals, bring down our 2 and multiply, we're going to be left with just the 25 dH dt. And now we can plug in what we know. So dV dt was 0.3. The height at which our instant we're caring about is 0.3, or excuse me, 1.5. So I'm going to plug in 25, 1.5, and then we're looking for dH dt, okay? When I multiply and then get dH dt by itself, we get 0.008. Sorry, my pencil is losing some lead. And our rate, height, is a unit of meters, and it's a rate, so in our unit of time is per minute. So meters per minute. Okay, a spherical balloon is inflated at a rate of 10 cubic meters per minute. Find the rate at which the surface area of the balloon is increasing when the radius of the sphere is 3 meters. Okay, again, I see a cubic meter, so that is a dV dt is 10 cubic meters per minute. Okay, and we want to find at what rate is the surface area. So we would like to find a ds dt, and we're given a radius instant when the radius is 3. Okay, so volume and surface area are actually two different equations, right? Volume and surface area. Here's our volume equation of a sphere. Our volume is 4/3 pi r cubed, and our surface area equation is 4 pi r squared. Okay, so I am given a rate in terms of volume, but I'd like to find ds dt. So this is that instance where in your directions, kind of at the beginning of our last video, there were some steps, and it says sometimes you might use more than one equation. Okay, well, I know I'm going to want to end up using this one because I need to find ds dt. That's like what I'm looking for. So here what I'm going to do is I'm still going to differentiate both equations. So let's go ahead and do this. So we've got dv dt equals, when I bring down my 3, the 3 goes away, and we're left with 4 pi r squared, okay, and then dr dt. And if I differentiate here, ds dt, bring down our 2, we get 8 pi r dr dt. Okay, so what I'm going to do here, because both of these equations have dr dt, and I want to end up using this one because I'm looking for ds dt, right? That's what I want to find. I'm going to go ahead and solve this one for dr dt. So I'm going to divide both sides by 4 pi r squared. Okay, so why would I do that? Well, because dr dt is also in this equation, but this one I can put in the rate that I have in terms of volume. So we're going to take this and we are going to substitute in right there. Okay, so now I have ds dt, which is what I'm looking for, equals 8 pi r times dv dt over 4 pi r squared. Now, this actually simplifies pretty nicely, you guys. The pi's are going to cancel, and then 4 goes into 8 2 times. And then one of the r's cancels with that r, so I'm left with 2 dv dt over r. And this is what ds dt is going to equal. So now I can plug in the two other pieces I know. We know dv dt is 10, and r for this instance is 3. So we get ds dt equals 2 times 10 over 3. Okay, or 20/3. And again, this is a surface area. Area always has square units, so this is going to be square meters per unit of time. Okay, and we're just going to hit those two examples in this video. Thanks for watching.